Swayam Prabha. Digital India. Educated India.
Hello students, welcome to another class of this course, Thermal and Statistical Physics, and we'll maybe quickly recap what we were doing last time. So in the last lecture we basically started with the limitations of first law of thermodynamics, right. So we argued that even though first law of thermodynamics is useful, it talks about conservation of energy, but it cannot really tell us how the processes evolve as a function of time, right. So we gave some examples like how spontaneously the molecules in this room, they cannot really cool down, half of the molecules can't really cool down and other half can't really heat up spontaneously, right. So all these processes, all these situations, first law is incapable of explaining, all right. And we came up with the two statements of second law, which are basically driven by our daily observations, right. And the first statement that we talked about was Clausius statement, which said that no process is possible whose only purpose is to transfer heat from cold body to a hot body. Okay. So any process which is only transferring heat from cold body to hot body or making cold body cooler and hot body hotter, that process is forbidden, right. For example, like I said, we never really see a piece of ice cube or a cup of water freezing spontaneously to ice, right, at just room temperature, right. So all those processes are just not possible. And also the Kelvin statement, which is another statement of second law, which says that the complete conversion of heat into work is also not possible, or in other words, we cannot convert heat into work with 100% efficiency, all right. And then we slowly, okay, so maybe I can write. So first one was Clausius statement, Clausius statement, which says no process possible which transfers heat from cold to hot body, right. Or I should be a little bit careful, no process possible whose only function, only purpose rather, is to transfer heat from cold body to a hot body, right. So that was the Clausius statement, and Kelvin statement was as follows. So the conversion of heat into work happens with certain efficiency eta, where eta is always less than 1. Okay. So you cannot have 100% efficient process which can convert heat into work, right. And slowly we basically came up with the concept of Carnot engine, right, which was itself based upon two postulates, that that heat can only flow from hot body to cold body, right. And also the other postulate was, the heat flow stops when the temperature of two bodies become equal, right. And there we saw that a process which is happening between two reservoirs kept at temperature Th and Tl, right. So there we saw that the efficiency of such a process is basically given by Th1 minus TL by Th. okay. And essentially this is how that process looked like. So, we have two isotherms and we have two adiabats. Isotherms are kept at temperature TH and TL, and heat is being absorbed along the first step, which is first isotherm. So, QH is absorbed, and then you have an adiabatic process, you have another isothermal process and another adiabatic process, and QL heat is dumped into the cold reservoir, right. And the other schematic that we drew looked as this. So, look like this. So, you have so we have hot reservoir, right. So, maybe I can do here. So, we have a hot reservoir which is extracting heat QH, and the engine, the Carnot engine is extracting heat QH from the hot reservoir, and it is dumping heat QL into the cold reservoir, and in turn it is doing a work, right. And the efficiency is given by 1 minus TL by TH. Okay. And later on we also saw that since Carnot engine is a reversible quasi-static process, we can also run it backwards, right. So, we just turn the direction of these arrows, in which case, so this is the Carnot engine, right. And we also talked about what we call as the refrigerator, right. So, this is TH, you have a refrigerator and we have a cold reservoir which is kept at a lower temperature TL, and the purpose of this process is to extract heat QL from the cold reservoir, in which case obviously we have to do certain work on the refrigerator, and in turn there is a heat QH which is dumped into the hot reservoir. And in this case we defined another quantity which we did not call it efficiency, we called it the coefficient of performance, and we saw that the coefficient of performance of a refrigerator is TL divided by TH minus TL, and we can see that this efficiency can be greater than 1, and the reason for that is because according to Kelvin's statement, the complete conversion of heat into work is not allowed, but the other opposite is true, right. So, you can convert work completely into heat, all right. So, let us continue with those ideas in this class, right. So, let us define what is known as a Carnot theorem, right, and it goes as follows. Okay. So, this basically means that the Carnot engine, the reversible, okay. So, maybe among all heat engines operating between temperatures TH and TL, where TH is greater than TL, the Carnot engine has the highest efficiency, has the highest efficiency, has the highest efficiency. Okay. All it says is there is no other engine which exists which is operating between two temperatures, two reservoirs at TH and TL. The Carnot engine has the maximum efficiency and all other engines have a lower efficiency than that, all right. So, how do we prove that? Okay. And in order to prove it, we will go by the concept of proof by contradiction, right. So, it's called proof by contradiction. Okay. And how do we go about it? All right. So, let us say, so we claim that there exists an engine, let us call that engine E, which has a greater efficiency than the Carnot engine. Let me just call it Carnot engine as CE, all right. And what does that mean? Okay. So, say we have an engine, okay. So, we have this hot reservoir, right. So, let us call this TH, and we have a cold reservoir, let us call this is TL. So, what it means is we are claiming that there is an engine, okay. So, there is this engine that we are claiming that it has higher efficiency than Carnot engine, and this is the Carnot engine, okay. This is the Carnot engine, okay. And what do engines do? They basically extract heat QH from the hot body, right, and dump certain heat QL into the cold reservoir, and they do some work, right. And our claim is that the efficiency eta E of our claimed engine, which we are saying has higher efficiency, again you can see that it is given by W divided by QH, right, and let us for simplicity or for okay, so let us call this QH prime rather than QH, right. So, this is the efficiency of the claimed engine which has higher efficiency, and we know that the Carnot the efficiency of Carnot engine, which I am denoting as eta CE, is also equal to W divided by QH, right. So, let us say we have another Carnot engine which is extracting heat QH from the hot reservoir, throwing heat QL into the cold reservoir, and it is also doing certain work, and we are claiming. So, our claim is that claim eta E is greater than eta CE, right. And what does that mean if we just plug these things in here? So, that means W divided by QH prime is greater than W divided by QH, or this means QH is greater than QH prime, right. So, if our claim is true, then the QH has to be greater than QH prime, all right. Okay. So, so what do we do? Okay. So, let us do one thing, right. So, what we can do is we can attach these two engines together, okay. So, what that means is the work that is extracted from our claimed engine, which we are saying has a higher efficiency, we can use that work to run a Carnot engine in such a way that this engine basically becomes a refrigerator, right. Remember, in a refrigerator we do work on the working substance, it extracts heat from the cold reservoir and dumps heat into the hot reservoir, right. So, therefore, in this case the Carnot engine will act as a refrigerator, and it will instead extract heat QL from the cold reservoir and dump heat QH into the hot reservoir, okay. Okay. So, therefore, what we can do is now we can, so basically I am attaching these two engines together. Now, we can apply the first law of thermodynamics to this diagram, right. So, basically from applying first law of thermodynamics, right. So, clearly we can see that in this case W has to be equal to QH prime minus QL prime, looking at the engine E, right. And again, since we are doing work W on this system, this QH has to be equal to also and QH has to be equal to W plus QL, or which basically means W has to be equal to QH minus QL, all right. So, since W is common factor in both these equations, we can now equate right hand sides of these, okay. So, therefore, that implies that QH, so basically QH prime minus QL equals QH minus QL, QH prime minus QL prime, sorry, QH prime minus QL prime equals QH minus QL, or let me write it in this way, QH prime minus QH equals QL prime minus QL, all right. Okay. So, now remember what our claim is. So, we are claiming that eta E is greater than eta CE, which basically means QH is greater than QH prime, right. So, since QH minus QH prime is less than 0, and that implies your QL prime minus QL will also be less than 0. Sorry. So, QH minus QH prime, okay, so let me change, sorry. So, this is QH prime minus QH is less than 0, right. So, QH prime minus QH is less than 0. So, that means your QL prime minus QL is also negative, okay. Or we can write it in a slightly even better way, that QL is greater than QL prime, okay. So, what we are saying is that if the efficiency of engine E is greater than efficiency of the Carnot engine, the heat QL has to be greater than QL prime. Now, let us see what is QL and QL prime, right. So, remember QL is the heat which is being extracted from the cold body, and QL prime is the heat which is dumped into the cold body, right. So, now I just want to think about it. Now, now just assume that we do okay. So, let us call this as a composite engine, right. So, say we make an engine which is a combination of an engine E and Carnot engine put in series with each other, and we basically hide it under a hood, and when we attach it to two reservoirs which are kept at TH and TL, the net effect is that the amount of heat which is being extracted from the cold reservoir is greater than amount of heat which is dumped into the cold reservoir, right. So, that means, so this basically implies, right. So, this statement implies that there is net heat which is extracted from the cold reservoir, right. And why is it forbidden? Because this process is happening spontaneously, right. We are not really, okay. So, as you know, such a process where you are actually extracting heat from the cold body to hot body requires certain external amount of work to be done, right. But we are not really doing it. So, this process is spontaneously extracting heat from the cold body. So, therefore, this goes against the Kelvin's so basically the Clausius statement, right, that no process is feasible whose only purpose is to extract heat from cold to hot body. So, therefore, this is forbidden, right. This is against second law. So, let me write it against second law, right. So, therefore, this is not practical situation. So, since this is not possible, the claim that we started with is also not possible, right. So, we are contradicting ourselves. So, therefore, eta E has to be less than eta CE, and this is the proof by contradiction. Okay. And that basically implies that and this basically is the statement of Carnot theorem, that all the engines which are operating between two certain temperatures TH and TL, the Carnot engine has to have the maximum efficiency. Okay. So, let us now try to, okay. So far we have been, we have looked at various things. So, we have slowly transitioned into the second law statement, and we are now trying to understand processes, why certain processes they do not occur in nature, right. But we have not really understood it really well, right. So, what is that which is really stopping certain processes from happening, right. So, let us try to understand that, and now I will bring the concept of entropy for the very first time in this course, right. So, basically next thing that we will do is concept of entropy from Carnot engine. All right. So, again, like I gave you few examples last time as well. Like I said, the one half of the room cannot really spontaneously cool down, then the other half, if I mix coffee and milk, the coffee and milk cannot really spontaneously demix, right. So, it has to, so there is a direction in which certain processes always evolve, right. If I shatter a piece of glass, it will never really join back, or if I spray a bottle of perfume and the molecules will diffuse around and they will be homogeneously covering the entire room, but all those molecules cannot really go back into the perfume bottle, right. So, we already know there are certain processes which only evolve in certain direction, okay. And how do we understand that, right? And the answer to that question is entropy, okay. And let us basically see how we can come up with the concept of entropy from this formulation from this Carnot engine that we just discussed, okay. Okay, so basically let me write. So, what I am saying is the entropy, which I will define very soon. Entropy is a mathematical concept that emerges out of Carnot process, okay. And let us try to see how that happens, okay. So, I will draw this indicator diagram of the Carnot engine once more. So, you have pressure, you have volume. So, we have two isotherms, we have two adiabats, right, and our process is happening between two temperatures, TH, which is a hot reservoir, and TL, which is a cold reservoir, and it is again like we saw last time, it is a cyclic process which is happening between these four states, right. So, you first isothermally expand from volume VA to VB, then you adiabatically expand from VB to VC, then you isothermally compress your gas from VC to VD, and then you adiabatically compress your gas from VD to VA, right. And we also saw that in the first isotherm, the system is absorbing heat QH from the hot reservoir, and in the second isotherm the system is dumping heat QL into the cold reservoir, right. And another interesting result that we got when we were discussing about the Carnot efficiency was as follows. So, we saw the ratio of heat QH to QL is basically equal to the ratio TH divided by TL, okay. Now, let me, okay. So, what is its physical significance, right? So, remember so let us try to understand what are the state functions in this process, okay. So, what do I mean by that, right? So, say I start my system from state A, which is at certain pressure and volume. I undergo one complete cycle of the Carnot process and I come back to the state A, all right. And one important point or thing about state A is that the energy, the internal energy of the system at state A is only dependent on the parameters P and V, right. It does not really depend which path I have taken to arrive at this point, all right. So, therefore, what I am saying is internal energy is a state function, right, which means the internal energy of the system at point A is independent of which path I followed to come to this point, right. So, therefore, in a cyclic process which goes from A to B, B to C, C to D, D to A, once I complete one cycle, the internal energy of the system is a conserved quantity, right. So, that means after a complete cycle, after completing, okay. So, after completing one Carnot cycle, internal energy remains conserved. Okay. So, we are sure that there is internal energy which is a state function which remains conserved after undergoing one Carnot cycle. Now, let us ask whether this is the only conserved quantity, right. Are there other conserved quantities in this process, okay. Are there other equations, state functions that we can define? All right. Okay, so let us see, let us check that, right. So let us now turn our attention to a quantity. Okay, so let us turn our attention to a quantity which is the ratio of heat to temperature, all right, and let us see what happens to this quantity over one complete cycle, right. Okay, so let us concentrate on this quantity. So from A to B, right. So from A to B, what is Q divided by T? So from A to B, Q for the Q by T is basically equal to QH divided by QH divided by TH, right. And why is this positive? Because system is gaining heat from the hot reservoir, so there is a plus sign in front, right. So for process A to B, Q by T is QH by TH, right. What about for process B to C, right. So remember, the process B to C is a adiabatic process, so therefore there is no heat exchange, right. So Q in numerator is 0, so this is 0, all right. What about C to D, right. So in this case, the system is dumping heat QL into the cold reservoir at while maintaining its temperature TL, right. So this is minus QL by TL, and from D to A, which is another adiabatic process, so this is equal to 0, right. So therefore we can see that if I sum this quantity which I just called as Q by T over this one complete cycle, so what would that be? Okay, so let me call that the sum of Qi by Ti, where I basically stands for the processes A to B, B to C, C to D, D to A, and we are completing a Carnot cycle. Okay. So this sum over this Carnot cycle is basically sum of all these values. So this is QH by TH for A to B plus 0 for B to C minus QL by TL for C to D, and for D to A it is again 0, right. And what is this value? So remember, we know QH by QL is TH by TL, and this also means QH by TH equals QL by TL, which basically means both are equal, so they cancel out, right, and this is 0, all right. So now let us give it certain name, right. So let's call, so say, so define and let's give it a name. We give it a name which is entropy. Entropy, which is denoted by symbol S, as the ratio of heat to the temperature, right. And this is like some kind of thermodynamic definition. Okay. So if we define entropy in such a way, then we know that the change in entropy, which is delta S over a Carnot cycle. So let us call this delta S I, which is this Qi by Ti over this Carnot cycle, and we just checked that this is 0. Okay. So that means for a reversible Carnot engine, since delta S is 0, S is a conserved quantity. So therefore, not only the internal energy of the system is conserved, but this newly defined quantity which we define entropy, which is the ratio of heat to temperature, that also remains conserved. Okay. So this is again, like, this naturally comes out from this Carnot process, right. We had no insight into what's going on, right. So it turns out this quantity Q by T is another conserved variable, right, because it's also a state variable in that sense, all right. So let us see how it is useful. Okay. So now, like many of you probably already know, that we always say that processes evolve in the direction of increasing entropy. Okay. So this entropy is that variable or is that parameter which can now perhaps give us a clue why certain thermodynamic processes always evolve in one direction, right? Why perfume molecules, they never go back into the perfume bottle spontaneously, because we can argue that in that case maybe S, something happens to this quantity S, right. So, let us see what is that particular property of this S which can basically answer this question, right, why certain processes evolve in only one direction. Okay. So, let us apply this to a very simple process, okay, which we already know is irreversible, all right. So, basically let us apply this to this process. So, we already know if we have a hot body kept at temperature Th and we have another cold body kept at temperature Tl, we know that heat flow will always be from hot body to the cold body, and let us say heat flow is given by Q. Okay. So, and we are saying this is a process which is allowed, right. Okay. But what we are also arguing is that the reverse is not possible. Okay. So, this process cannot really proceed in this direction. Okay. So, the heat cannot really flow from cold body to hot body spontaneously. Okay. So, this is basically forbidden. Okay. So, in that sense this is an irreversible process because it always happens in one direction. Okay. So, now let us try to calculate this quantity delta S for such a process. Okay. So, let us call this process number 1, process number 2. 1 is where the heat is flowing from hot to cold and 2 is where heat is flowing from cold to hot, right. So, for case 1, which is this process, okay. So, let us calculate this delta S, right, and this delta S is basically sum of Q by T, right. So, let us call it Qi by Ti, right, and this is just, there are just two processes. So, when heat goes from hot body, so this is basically Q divided by Th, right, and we have to put a negative sign here because heat is being extracted out of the system, right, and heat is dumped into the cold reservoir. So, this is Q divided by TL, and this you can very easily check, this is Q times Th minus TL divided by TL, okay, TL, and we can see that since Th is greater than TL, in this process the delta S or the entropy change is positive, right. So, now let us see what happens in the second case, okay, case 2. So, we can check that delta S in this case is basically equal to, the heat is dumped into the hot reservoir, right. So, therefore, okay, so therefore, this is Q divided by Th and heat is extracted from cold reservoir. So, this is Q divided by TL, and this is also equal to Q times TL minus Th divided by TL, and you can see this quantity is less than negative. Okay. So, this basically gives us a clue, right. The process which is allowed in thermodynamics, is it true that the entropy change is always positive for that process, and the process which is forbidden, which we know cannot really happen, is it always true that the entropy change is negative? And it turns out that is what it is, right. So, this is really this variable entropy which can basically solve the mystery why certain processes are reversible and why certain processes are irreversible, right. So, okay, so maybe we can summarize. So, we check that for reversible Carnot engine, right, we just checked that delta S is 0, right, delta S is 0 for irreversible processes. Delta S is always positive, and for forbidden processes like these ones where the heat is flowing from cold to hot body spontaneously, delta S is negative, right. So, these are the processes which are reversible, these are the processes which are spontaneously irreversible, they always go in certain direction, and these are the processes which are forbidden. Okay. And basically we can together we can say that the processes which are allowed in the nature, they must follow this property that the change in entropy should always be greater than or equal to 0. Okay. So, in that sense the entropy also provides us with a very neat definition of time, right. So, it basically sets the direction of time, right. So, if I am mixing coffee with milk, so the brown portion and white portion will spontaneously mix and we will end up with a like light brown colored liquid, right. And this process cannot really go in the reverse direction. And if you record a video of this process like coffee and sugar and milk mixing, and if I play that video backwards, you will say that there is something wrong, right. So, you will know that I am playing that video backwards because that process does not really happen in nature, it is forbidden, all right. So, maybe I can write that entropy also sets the direction of time arrow. Okay. So, why time proceeds in certain direction, okay, and it goes into the direction of increasing entropy. Okay, so let us move on to new concept, okay, again related to entropy, which is known as Clausius inequality. So, Clausius inequality. Okay, and it is also known as Clausius theorem. Okay. So, again I will go back to the Carnot engine, right. So, remember this is how we understood Carnot engine on the indicator diagram. So, this is PV, we have 2 isotherms, we have 2 adiabats, right. Since we said that Carnot engine is a reversible engine, so, so again it is operating between 2 temperatures TH and TL, and in this first isothermal process it is extracting heat QH, let me call it reversible now, from the hot reservoir, and dumping heat QL, let me put this station reversible on top of Q, which is QL, it is dumping heat QL reversible into the cold reservoir. Okay. And when I draw this solid lines, you mean so we understand that this is a reversible process, but how would a irreversible Carnot engine look like, right. So, that is simple, like if you remember I said that an irreversible process on an indicator diagram is shown as a dashed line. Okay. So, instead of solid line you just draw these dashed lines. Okay. So, we can't really connect these points with a solid line if it is an irreversible process. Again this is hot temperature TH, this is TL, and in this case the system is extracting heat QH, let me call it irreversible, from the hot reservoir and dumping heat QL irreversible into the cold reservoir, all right. So, clearly in this case, okay, so we can define the efficiency of the reversible engine, which is as follows. So, this is the work extracted in the case of reversible engine, this is W divided by QH reversible, and from first law we can write QH reversible minus QL reversible divided by QH reversible. Okay. Similarly, we can define the efficiency of the irreversible engine as eta irreversible, and this is also equal to W divided by QH irreversible, and from first law we can write it as QH irreversible minus QL irreversible divided by, okay, so this should be reversible, okay, and this is QH irreversible. Okay. And we also know from the Carnot engine that the reversible Carnot engine has the highest efficiency when work operating between 2 temperatures, right. So, from Carnot theorem, we know eta reversible has to be greater than eta irreversible, right. And now we can just substitute these values here, and all that means is QH. So, QH okay. So, QH irreversible minus QL irreversible divided by QH irreversible, sorry. So, this is QH is less than QL reversible, sorry, QH reversible minus QL reversible divided by QH reversible. Okay. So, all I am saying is so this eta reversible is greater than eta irreversible. Okay. All right. And we can simplify this in this way. So, this becomes 1 minus QL irreversible divided by QH irreversible is less than 1 minus QL reversible divided by QH reversible, okay. Or we can write QL reversible by QH reversible is less than QL irreversible by QH irreversible. Okay. All right. But we know, so from Carnot engine, or we can say for a reversible Carnot process. So, what is the ratio of QL reversible divided by QH reversible, and this we know this is equal to TL divided by TH. Okay. So, therefore, if we put it here, so therefore, we can conclude that QL irreversible divided by QH irreversible is greater than TL divided by TH. All right. Or we can again write it in a different form, that QH irreversible divided by TH is less than QL irreversible divided by TL, and this is the result that we have. Okay. So, sorry. So, this is what we get. Okay. So, this is what we get. All right. So, therefore, now what we can do is we can now see okay. So, now we can basically try to calculate the similar quantity, okay, that we defined, similar quantity to this that we defined for a reversible Carnot process, right, and we saw that this quantity is 0. So, okay. So, let us now do this for an irreversible process, right. So, considering this, so therefore, for an irreversible Carnot engine. Okay. So, let us define that as the cyclic integral of all the dq divided by t for an irreversible process. So, that is equal to for this Carnot process, that is QH irreversible divided by TH, right. This is for the process, for the first isothermal process. For the adiabatic process, we get 0 plus 0 minus QL irreversible divided by TL, right. This is for this isothermal compression, and plus 0. Okay. And this is essentially, okay. So, what do we have? We have QH irreversible by TH minus QL irreversible by TL, and we know if I take this to this side, so QH by TH irreversible minus QL by TL irreversible is a negative number, right. So for this case, so you can see that this is not equal to 0, but this is less than 0, right. But we okay, so but whereas this quantity for a cyclic process is exactly equal to 0, okay. Sorry, for a reversible Carnot process this is exactly equal to 0, but whereas if our engine is irreversible, this quantity is less than 0, okay. So therefore we can combine these two results and we can argue that the quantity dq by T is either less than or equal to 0 depending upon whether the process is irreversible or reversible. For an irreversible process, this quantity is negative over a cycle, but this quantity is equal to 0 if the process is reversible. If it is irreversible, it is negative, okay. And this statement or this equation is known as Clausius' inequality. Okay, so this is an important result. Okay, so this is an important result. So let us try to understand its implications, right? Okay, so let us so the next thing that we'll do is basically the principle of increase in entropy. Okay, so increase in entropy principle. Okay, so let us apply this Clausius' inequality to a very simple minded process and let us see what do we get. Okay. So the process looks as follows. So say we have this, again we have certain indicator diagram where the system is prepared at certain state 1 and there is another state of the system which is 2. Say we go from state 1 to state 2 irreversibly, right. So remember I am not drawing a solid line. So this is how the process evolves, but when we come back from 2 to 1 we do so reversibly, right. So I draw a solid line. So therefore 1 to 2 is an irreversible process, okay. So I can write, so 1 to 2 is an irreversible process. Irreversible process, whereas 2 to 1 is a reversible process. Okay. So therefore let us apply Clausius' inequality to this, right. So if I apply the inequality over this loop, so this integral dq by T evaluated over this complete loop is basically this integral evaluated from 1 to 2 where the heat dq is irreversible, okay. So let me call irreversible divided by temperature T plus the process 2 to 1 where the process is reversible. So let me call this dq reversible divided by T. And we see that since one arm of this this path is irreversible, this inequality has to be less than 0. Okay, so it can't be equal to 0. It would have been equal to 0 if this was also a reversible process, but because it is an irreversible process, this is negative. Okay, and what that means is, that means this process 1 to 2 dq irreversible divided by T plus, and now what is this quantity, right. So this quantity where the process is happening from 2 to 1, and since this is a reversible process, we can and we know the ratio of heat to temperature is entropy. So this integral will basically give me S1 minus S2, that is the entropy, since it is a state function, entropy of the system at point 1 minus entropy of the system at point 2, and this is negative, right. Or in other words, I can write S2 minus S1, if I take it to the other side, is greater than 1 to 2 dq irreversible divided by T. Okay. So, this is an important result. Okay. So, this 2 is here. So, this is an important result. Okay. So, let us see what is its implication, right. So, let us now try to apply this process to our universe essentially, all right. So, okay. So, let us say we have a system. Okay. So, remember when we defined system. So, we said that system is the subset of the universe which we are interested in, and everything outside is rest of the universe, right. So, let me now draw universe in some sense. Okay. So, let me just draw universe. Okay. So, and remember the first law of thermodynamics. So, there we assumed that no matter what happens, the total energy remains conserved, right. So, that means whatever happens to this system, the total energy of this entire universe remains constant, right. So, in that sense, if I call this box in which my system is sitting, right. Okay. So, where my system is sitting. So, remember this is system, this is rest of the universe, and this entire the big box is universe, right. So, my system is universe minus rest of the universe, all right. And since from first law of thermodynamics we assumed that all the processes in this universe, they conserve the total energy, that means this universe is a isolated system, right. So, from first law, this the first law implies that the universe is an isolated system, and all the processes that happen in this universe, they are adiabatic, right. So, what I am saying is, if I apply this this result to the universe, since universe is an isolated system, there is no heat exchange which is allowed. So, dq irreversible has to be 0. Okay. Since it is an adiabatic system, it is not really in contact with any reservoir or anything. So, the total energy of this universe is constant, and that is, and since we are not really doing any work, that means the dq featuring here has to be 0. Okay. So, therefore, what I am saying is for a universe, okay, so all processes inside the universe are adiabatic. Okay. So, whatever is happening inside the universe, it is not really exchanging heat outside the universe, because there is nothing outside the universe, that is the whole thing that we know, right. So, therefore, dq irreversible is equal to 0, all right, when applied to this universe as a system. So, remember I am now thinking about universe as a system, right. So, this entire system dq irreversible is 0, and if I put this here, then what I get is S2 minus S1 has to be greater than 0. Okay. So, that means so when I move my system, now I am talking about this system, from state 1 to state 2 in an irreversible manner, the entropy change has to be positive, because the net processes happening in the universe are adiabatic. Okay. So, I hope this concept to be very clear in your mind. Okay. So, there should be no confusion, all right. So, this is an important result, all right. So, an irreversible process always leads to net entropy production. Right. and in some sense we are basically getting the same result that we checked here also, right. We saw that when the heat is flowing from a hot body to a cold body, that process automatically ensures that the entropy change is positive, which means there is a net production of entropy. And similarly, we proved the same thing from Clausius's inequality, that if we prepare a system in such a way that it goes from state 1 to 2 irreversibly, that process has to create certain entropy, and that is because of the first law, because universe is an isolated system, it cannot really exchange heat with anything else, all right. Okay. So, therefore, we can kind of summarize whatever we learned about our universe so far, right. So, in summary, okay, in summary, so these are the statements that I am telling about the universe. For the universe, the first law of thermodynamics implies that the total energy of this universe remains constant, and from the second law of thermodynamics, right, when we apply the ideas of second law, this implies that the total entropy change of this universe has to be greater than or equal to 0, where greater than 0 is for the processes which are irreversible and equal to 0 is for the processes which are reversible, all right. And of course, this basically takes us to a more fundamental kind of questions, right. So, we know that we exist, right. So, we are out of equilibrium, we are producing entropy all the time, right. So, that means our universe must have been created at a very low entropy state, right. We all talk about Big Bang theory and so on, right. So, we say that the universe was basically a singular point where all the matter was concentrated, and since it was concentrated in small volume, it had very low entropy, right. So, just imagine one way or the other, I pick all the gas molecules in this room and confine it to single point and let it evolve, right. And that process, so say all the molecules are in this tiny area, in tiny volume, and now they are like expanding, right. And this process is irreversible because the molecules cannot really spontaneously come back to this point, okay. So, therefore, the entropy of this universe, whoever created this universe or whatever process created our universe, the entropy was very low, okay. And ever since the creation of this universe, the entropy is constantly increasing, right. So, all the processes that are allowed in the universe, they only lead to production of entropy, right. And all the equilibrium processes which are also reversible processes, the entropy change is 0, all right. So, this is an interesting result, an important result that we have got after going through the concepts of Carnot-Engine, the statements of second law, all right. So, so basically in the next class we will try to continue with the concept of entropy and yeah, so see you in the next class.